Welcome back, class. As mentioned in this sequence of videos to start with, we're going to be talking about the 12-fold way. So we're going to be answering this question: how many ways can I put m objects into n boxes subject to these things? And so the first one I want to do is the case where the objects are distinct, the boxes are distinguishable, and there is no restriction. So that means for each of the m objects, I have to choose which box to put it in. Which means, by the way, that we could really frame all of this in terms of counting functions from a set of m distinguishable objects to a set of n distinguishable boxes. So the distinguishable box in each category is really counting functions. And so in the distinguishable case, we're just literally counting functions from a set with m elements to a set with n elements. And then we can figure out, okay, if we have to put at most one object per box and at least one object per box, we can figure out what restriction we're imposing on this kind of function. Okay, so to start with, let's just do the no restriction. Functions from m to n, how many of them are there? Well, for each of these m things, I have to choose which of the n places to send it to. So that is going to be n to the m total ways. Okay, so that is our distinguishable category. Okay. So I'm going to leave the rest of these for now. We'll talk about these later. Let's leap onward, though, and let's talk about a couple of the ones that are a little bit easier. So, namely, there's a couple of these that are kind of ridiculous. Namely, let's now look at this column of this paper and think about what it's asking us. So here we're asking the question, if I want to put m distinguishable objects into boxes, and so this column I'm putting objects, distinguishable or not, into boxes, except the boxes are indistinguishable. And then there's at most one object per box. Okay. So what's going to happen? Well, if the objects are distinguishable and the boxes aren't, well, then I'm going to put each object in a box. But then that's it, right? So if, let's say, m is 3, n is 4, I've got my 4 boxes, and I want to put my numbers 1, 2, 3 in these boxes, but I'm not allowed to put more than one number in a box, because that was our restriction for this page, is we're talking about at most one object per box. So I'll go ahead and say, okay, I'll put 1 here, 2 here, and 3 down there. And that provides the illusion of choice, because it looks like I did something. Except remember, the boxes are indistinguishable. So in fact, I didn't actually do anything. This is exactly the same as if I put 1 here, 2 here, and 3 here. Okay. Which means if m is 3 and n is 4, how many ways are there to put m distinguishable objects in n indistinguishable boxes, such that there's at most one object per box? Well, there is exactly one way to do it. Okay. And so, in fact, that's always going to be the case as long as it's possible at all. Okay. When is it possible at all? Well, it's possible at all as long as m is less than or equal to n, right? Okay. So it is 1 if m is less than or equal to n. Okay. In which case, there's only one possible way to do it. And it is 0 if m is bigger than n. Okay. That's really a consequence, if you want, of the pigeonhole principle. I can't possibly write down a way of putting these objects into the boxes if there's more objects than boxes, and I'm not allowed to put more than one object per box. Okay, let's, while we're here, also think about this corner. So we're again putting we're again putting things in indistinguishable boxes, at most one per box. But now the things themselves are indistinguishable. Well, if you want, we can draw the same picture before, except now instead of thinking about three distinguishable things, we're now thinking about, say, 3 dots. And I think indistinguishable, I like to think about dots. Okay, and so now we can take these out. And so maybe I put a dot here, I put a dot here, and I put a dot over there. But just like before, we've provided the illusion of choice because it seems like maybe I could have put them here, here, and here instead, or whatever. But the boxes themselves are indistinguishable. So just like before, here, if it's possible at all to put one ball in in some number of boxes, then there's exactly one way to do it because the boxes are indistinguishable. And otherwise, it's impossible and there's 0. Okay, and so, in fact, literally, the answer here is exactly the same. Namely, it is this. It is 1 if m is less than or equal to n, and 0 if m is greater than n. Okay, so I'm going to leave that there for now. We filled in 3 of the boxes so far. Next time, we're going to figure out where our 2 special counting numbers show up in this diagram. So we have these 2 special sequences that I'll remind you of. We have the big S Stirling numbers, and we have the little p partition numbers. And so let's remember for next time what these are and where they're going to go. All right, until next time.